Hello, everyone. I'm Jiaqi Guan, currently a master's student at Guangdong University of Technology. Here I'm glad to present our work, Dual-Level Contrastive Learning Network for Generalized Zero-Shot Learning. As we know, traditional deep learning models usually require massive amounts of annotated samples for training, which is often prohibitive in real-world applications. Therefore, a more feasible paradigm, called zero-shot learning, is proposed to recognize new categories without demanding labeled training data from them. Zero-shot learning aims to transfer knowledge from labeled classes into new classes with the help of semantic information, so that the model can recognize new classes without available training data. Assume that the seen class set includes otter and tiger, while the unseen class set contains polar bear and zebra. During the training stage, both generalized zero-shot learning and zero-shot learning have access to the samples and semantic representations of the seen class set. According to the classification range, zero-shot learning methods can be categorized into conventional zero-shot learning and generalized zero-shot learning. During the test stage, zero-shot learning can only recognize samples from the unseen class set, for example, polar bear and zebra, while generalized zero-shot learning is able to recognize samples from both sets, for example, otter, tiger, polar bear and zebra. In this paper, we focus on the more challenging setting generalized zero-shot learning. Recently, the generative adversarial networks have been widely used in generalized zero-shot learning, which can compensate for the lack of training samples of unseen classes. Despite the promising performance, a significant deficiency in these methods is that they expose a large quality gap between synthesized unseen features and real unseen features and lack discriminative information. This problem is alleviated to a certain extent by some recent methods that employ contrastive learning to obtain a better embedding. However, these methods still fail to solve two essential issues of generalized zero-shot learning. Firstly, note that semantic characteristics vary in different categories, but these models cannot capture fine-grained cluster structure knowledge, resulting in poor quality synthetic features for generalized zero-shot learning tasks. Secondly, the guidance of generator learning is heavily biased to the seen classes, while the structural information from unseen classes is ignored. Consequently, the generator trained on seen features cannot reasonably settle the demand for generating authentic unseen features due to data variations. To tackle the above problems, we propose a novel dual-level contrastive learning network, DCLN, which jointly performs intra-domain and cross-domain contrastive learning to improve generalized zero-shot learning performance further, as shown. Part A illustration of existing contrastive learning-based methods, which merely focus on instance discrimination but fail to take the finer class-specific structure and the unseen domain into account. Part B illustration of center prototype contrastive learning, which is proposed to exploit the fine-grained cluster structures. Part C illustration of cross-domain instance prototype contrastive learning, which focuses on both source domain and target domain to avoid overfitting the classifier to the seen classes. In summary, our proposed DCLN intends to exploit not only intra-domain knowledge but also cross-domain knowledge using A, B, and C. As shown in the picture, our dual-level contrastive learning network is composed of three components. On the left side, the feature generator G aims to generate visual features with the semantic prototype A and the Gaussian noise, while the discriminator D is to distinguish generated one from real ones. Then, the function E is learned to map the visual samples into the embedding space. On the upper right side, the intra-domain contrastive learning, we use a projection head to further constrain representation quality. Simultaneously, a reasoning network R is introduced to measure the relevance scores between the semantic prototypes and data points. On the lower right side, in the cross-domain contrastive learning, we also employ reasoning network R to measure instance prototype contrastive loss across two domains. For the instance-level contrast, we propose contrasting between instances by efficiently leveraging the label information to encourage discriminative representations, which is different from conventional self-supervised contrastive learning that concentrates merely on instance discrimination. Analogously, for class-level contrast, the only positive semantic prototype is the one corresponding to the class which Z belongs to, while the remaining semantic prototypes are treated as the negative semantic prototypes. With such, we can formulate the class-level contrastive loss as follows. For center prototype contrast, we expect that the semantic information from the prototype can be well embodied in the synthesized data. So far, although a discriminator is incorporated to align the synthesized data distribution to the real one, we point out that it is actually a coarse-grained weak constraint. Specifically, D is oblivious to the cluster structure of each class such that the cluster of each class may be severely distorted despite a plausible marginal distribution. To tackle this deficiency, we propose a center prototype contrasting scheme to provide a stronger supervision signal for the generator learning, with the objective formulated as follows. We introduce cross-domain instance prototype contrastive learning to efficiently transfer knowledge from the source domain to the target domain and learn more discriminative features, which involves constraints in two directions. We propose to use class similarity matrix as the supervision signals to regulate the structural relation between seen class embeddings and unseen class prototypes. We can compute the contrastive loss from seen instance to unseen prototype as follows. To summarize, this function is the overall objective function of the proposed DCLN. Once the generator is well trained, we train the final generalized zero-shot learning classifier on the real seen visual features and the synthesized unseen visual features. Finally, the generalized zero-shot learning classifier strives to predict the corresponding class label for the test sample from either seen or unseen classes. We evaluate the proposed approach on 4 widely used datasets for generalized zero-shot learning tasks. We compare our DCLN with 2 groups of state-of-the-art models, non-generative methods and generative methods. Compared to generative methods, our DCLN consistently achieves the best performance in terms of H on 3 benchmarks, i.e., 69.3% on AWA1, 70.0% on AWA2, and 66.6% on CUB. Meanwhile, DCLN attains competitive results in terms of H on SUN with 41.7%. Compared to non-generative methods, our DCLN can significantly achieve better results by a large margin, especially on AWA2, CUB, SUN datasets. Meanwhile, we also observe that the performance of our method on accuracies tested on unseen and accuracies tested on seen is more balanced, which reveals the effectiveness of our model to mitigate the seen-unseen bias problem. We investigate the effectiveness of 2 key components in our model. From the reported results, it is easy to observe that both parts contribute to the overall performance. The cross-domain contrast provides a more considerable performance boost than the center prototype contrast on AWA1 and AWA2. This improvement may be attributed to the fact that AWA1 and AWA2 are coarse-grained datasets with reasonable discrimination for class attributes, which can provide helpful knowledge to transfer during the cross-domain contrastive learning process. The center prototype contrast is beneficial to improve the interclass grouping and decrease misclassification, resulting in favorable performance on the CUB dataset. We further study the influence of the parameters. It is observed that our model is insensitive to the choice of weight of seen instance to unseen prototype contrastive loss. Our model can achieve promising performance when weight of center prototype contrastive loss and unseen instance to seen prototype contrastive loss are within the proper range of 0.0001 to 0.01 and 0.0001 to 0.1, respectively. In this paper, we propose a novel dual-level contrastive learning network for the GZSL task. It exploits not only intra-domain information but also cross-domain information through contrastive learning. Generally, intra-domain contrast is developed to explore the fine-grained cluster structures, and cross-domain contrast considers the relations between 2 domains. As a result, our model can generate more discriminative features for generalized zero-shot learning and ensure explicit knowledge transfer across 2 domains. Extensive experiments on 4 benchmark datasets show the superiority of our DCLN. Thank you very much for watching this video.